In this video, we will be covering a number of advanced features offered by the Vital Systems Smart Aussie PLC and Gateway and VS Logic software. Please remember that everything shown in this video represents a product in development and is subject to change. This video is going to be split up into 3 sections. In the first section, I'm going to just cover a few basic features that we've yet to cover. In the second section, I'm going to explain the conveyor layout screen and go through the process of creating a fully functional system based on a conveyor layout diagram. In the last section, I'm going to explain the Smart Aussie's support for protocols such as Ethernet IP and Modbus. Let's get started. The first thing I'm going to cover is this: the platform system. If in the future we release new hardware models or new firmware that have different capabilities from the current version, they will be added here in this dropdown. You must have the matching platform selected in order to download your project to your card. VS Logic will offer to update the selected platform when a platform mismatch occurs, but selecting the proper platform when designing your system will ensure that it will be compatible with the target setup. Next to the platform dropdown are buttons for 2 features used in ladder editing: Find and Replace, and Cross-Reference. The Find and Replace feature works as you would expect. It allows you to search for and optionally replace a string of text in the ladder programs. The Cross-Reference feature compiles a list of all the addresses used in ladder programs and where and how much they're used. You can filter based on ladder and by type, and can jump directly to that address by double-clicking it. The last basic feature to cover is the comment system. After choosing an address for a contact or coil, you can write a comment for that address in the property box. All contacts and coils within the ladder with that type and index will now share the same comment. Use of this feature is a must for creating readable ladder programs. You can also set a description for the ladder here at the top of the editor window to explain the ladder's intended use. In this next section, we're going to create a functional system based on a conveyor layout diagram. In this picture, we can see we have merge and divert sections surrounded by accumulation conveyor sections. I'm going to start with a blank project for this demonstration. First, I'm going to need the actual ladder programs before I can create the conveyor sections in this demo. VS Logic comes with a number of sample programs by default, including the ones we need here. These are accessible through the Ladder Library feature. You can open the Ladder Library by either right or double-clicking on the conveyor type node, or by going to the Tools menu at the top of the screen. Here in the Ladder Library, you can easily save or load ladder programs to the library to quickly set up new projects. I'm going to select the ladder programs I want to add to my project, and then click here to bring them over. You can also export the library to a file, or import ladder programs for one of these files or other projects. The Ladder Library also keeps backups of the last 50 versions of itself, accessible by clicking this button here. Now that we have the ladders imported into our project, we're going to open the graphical conveyor layout screen by double-clicking here. As you can see in the diagram, there are 5 accumulation, 1 merge, and 1 divert conveyor sections. I'm going to create these conveyor sections by dragging the different conveyor types into the conveyor layout window, copying the diagram's layout as I go. Each conveyor type is assigned a unique color to help visualize the system layout. Now, we need to create interlocks between our conveyor sections to facilitate the flow of packages from one section to another. Interlocks allow for this by passing binary data between the 2 connected conveyor sections. For example, I could pass a bit from one section upstream to signify that the section's first zone is empty, or I could send a bit downstream to signify that there's a package ready for the next section. I'm going to create an interlock by first clicking this section, then pressing D. This designates that this is going to be this section's downstream interlock. Now I'm going to select another section and press U. This indicates that this will be this section's upstream interlock. There are a total of 8 different interlocks available to each conveyor section: up, down, left, right, and auxiliary 1 through 4. Each is chosen by their first letter except aux 1 through 4, which are chosen by the numbers 1 through 4. I'm going to now create interlocks for each of the sections I've created, matching the diagram as I go. Our conveyor layout is looking pretty good now, but I should show you how these interlocks are accessed inside the ladder. The file type XLK should be followed by one of these specifiers, and then that should be followed by either in or out to specify whether we're accessing the bit coming from or going to the connected section. Let's see it used in an example ladder. Here's a simplified version of the upstream logic used in our ladders. In the first rung, the section is sending its package available state to the downstream section based on the photo eye of its last zone. In the second rung, the section will turn on its last motor given that the photo eye is active and the downstream section is ready. Now, here's a simplified version of the downstream logic used in our ladders. In the first rung, the section is sending its zone ready state to the upstream section based on its zone 1 photo eye. In the second rung, the section will turn on its first motor given that the photo eye is not active and the upstream section has a package available. Remember that ladders are created with placeholders for the slave addresses, and must be mapped to real OSI addresses before they can be used. This technique allows the same ladder program to be reused at multiple locations in the conveyor. So now we'll be assigning our OSI MDR control cards in the slave maps of the sections that we created. I'll first connect my SmartOSI PLC and gateway board to VSLogix, then use the network browser to scan for slave cards. I'll add them to the slave list, then go to each conveyor section and fill out their slave map. The final step I'm going to do involves this feature, initialization parameters, or init params for short. This allows you to set the starting value for a ladder file when a section first starts running. The accumulation ladder I'm using is configurable and can have anywhere from 1 to 4 zones, selected by the value in register 0. I'm going to set an init param on each of these accumulation sections so that they will have 4 zones. I should also mention that these init params are only for section-specific ladder files, and that init params for global ladder files can be accessed in the master settings. Now I can download, run, and monitor the ladder program on my SmartOSI PLC board. As you can see, the register 0 for this accumulation section is set to 4, to signify that this section will have 4 zones. Now, I'm going to simulate a box moving along the conveyor. From within the OSI tab, you can simulate I/O while monitoring by right-clicking a slave and selecting Create Override. This will allow you to choose which inputs and outputs you want to override and what value you want to set them to. These first 2 slaves I map to the first accum section. This next one is mapped to the following merge, and these 2 are mapped to the following accum section. As I simulate the photo eye inputs, you can see the motor outputs activating to carry the box along the conveyor. The last thing I want to discuss is SmartOSI support for high-level protocols such as Ethernet IP and Modbus. The SmartOSI can operate in 2 modes, gateway mode and ladder mode. When gateway mode is enabled, the ladder logic of the SmartOSI will be turned off and will not run. Instead, the I/O of the OSI network will be controlled directly by an external master device. When ladder mode is enabled, however, the ladder logic will run and will be in control of the OSI network. In both modes, you must set up the OSI slave list to match your desired network. As usual, I recommend using the network browser for this step. Here's the format for the incoming and outgoing messages to and from the SmartOSI. The same format is used for both gateway and ladder modes. The message format from the master to the SmartOSI goes like this. The first 20 bytes are copied to the 5 control words between control word 40 and 44 for use in the ladder program. These bytes are unused in gateway mode. The next 64 bytes represent the commanded output data for the OSI slaves in gateway mode. The index of the byte corresponds to the OSI address you're referring to. The lower 4 bits of that byte define the outputs for that slave, while the upper 4 bits define the parameter. For the GX20 MDR control card, the parameter controls the analog output value of the motors. These 64 bytes are unused in ladder mode. The message format from the Smart OSI to the master goes like this. The first 20 bytes are copied from control words 45 through 49. The next 8 bytes represent the activated list for the OSI network, where each bit represents that OSI slave is online and exchanging data. The next 128 bytes represent the I/O of the slave. In addition to the output byte as before, there is also an extra byte for each slave, where the bottom 4 bits represent the slave's inputs, and the upper 4 bits represent the input parameter, whereas the output parameter represents the commanded value for the slave's parameter. The input parameter represents the actual value confirmed to be on the OSI slave. Here are the recommended settings for creating an Ethernet IP connection to the Smart OSI. The message size to the Smart OSI should be configured as 88, while the message size from the Smart OSI should be configured as 156. This completes the VS Logic's Advanced Features video. Thanks for watching.